So we're going to look at what happened in Flint, Michigan, and are there lessons to be learned around the country for even private drinking water systems. So this was a presentation that I had done to the American Public Health Association a few years ago. And I had to tell them I didn't have any commercial interest in this presentation. And the Kentucky Geologic Survey provided some data for this. Now, recent events, specifically Flint, Michigan, has raised public awareness about the possibility of drinking water being a viable route for lead exposure. And Dr. Edwards' work in Washington, D.C. and some other towns around the country has also helped show that. And those aren't the only towns where this may be happening. Now, pipe and weld corrosion are the principal mechanisms of lead transport in the water distribution system when lead is present. But lead can also even be in the faucets of brass fixtures and things like that that were installed even within the last decade or so. Now, the idea that pipes can corrode and cause lead exposure is not new. We know that pipe and weld corrosion are the principal means in which lead transport in the water system can make lead be present. Water engineers have known about this for a long time. I'm going to cite Langelier's paper to the American Water Works Association in 1936, where in the paper, here you go, you can see it right there, it said a rust coating not establishing calcium carbonate or limestone, right, is too porous. So rust inside the pipe is too porous and not sufficiently dense and continuous to offer protection. And to the contrary, once it starts, for example, it may even accelerate the corrosion in the form of pitting of these pipes. Dr. Edwards, back in 2004, not just from those recent videos I shared with you, he said that the water distribution system is going to be the key public health battlefield of the 21st century. And he includes in this corrosion of private plumbing. So what's happening in people's homes is deserving of special attention, since the health and economic impacts are probably of equal or greater magnitude compared to public systems. And there has not been an advocate working on the behalf of these consumers. And let's look at pipe corrosion and what it looks like. So this is from Mark Durno of the US EPA, and this was shown to Michigan Public Broadcasting during the Flint crisis. You can see what a corroded pipe looks like right here. And then here is a pipe with adequate corrosion control with that white powdery color on the inside. No corrosion control, corrosion control. Might I add, this happened over here on the left, this figure on the left, within like a year. The city of Flint thought corrosion might be happening. The state said, no, it's probably not happening, no way. Dr. Edwards gave the kids in the schools a nail test. We buy nails from a hardware store, we put the nails in drinking water from Flint and drinking water from Michigan, Detroit in particular. Detroit is where the people of Flint were getting their water before the emergency manager appointed by the governor of the state was brought into their town, who then told them that they needed to switch to Flint water. And there were some politics or some other reasons on why they may have been encouraged to do it, and you can read up more on that on your own. So in addition to chemical corrosion, so the pipes having corrosive water, microbes, once they get established in those pits, can also enhance corrosion. And guess what happens as the microbes start getting established? The chlorine is then more easily consumed because it's interacting with the microbes, and the microbes can then more easily establish in the system, and you can theoretically measure the health of the system by the heterotrophic plate count bacteria. The microbes too can enhance corrosion. As you add more and more microbes, they can get more and more numerous, resulting in more and more corrosion, which provides more and more habitat for the microbes, and it's a positive feedback loop. Now, all of this was preventable, okay? It was all preventable. So what was the cost per day of adding an anti-corrosion agent like zinc orthophosphate or some type of phosphate to prevent Flint's pipe corrosion problems? How much would it have cost? $1,400, $140, $1,400, or $14,000 per day? The answer is $140 per day. They could have prevented it. So how does a water plant know if their water is corrosive? Is this a really hard thing to figure out? So there's this big formula, the Langelier Saturation Index. Look at this thing. All these pKs in there, measuring calcium, alkalinity, log, gamma. Looks tough. But a lot of entities, including the American Water Works Association, make this type of calculation easy and free. And if you know your total dissolved solids temperature, calcium concentrations, alkalinity, pH, and so forth, you can calculate the Langelier Index. And then you can find out what your number is. And the Langelier Index, it will tell you if your water is likely to be corrosive or if your water is likely to be scaling. Scaling, if it scales too much, it'll clog up the pipes. If it's corrosive, it'll eat the pipes away. If it's corrosive with pipe corrosion control measures, you can stop this corrosion by adding an anti-corrosion agent. If it's scaling, you know you're going to have to figure out a way to get rid of whatever is causing the high amounts, sometimes calcium, from building up in the pipes. That's not good for people's water heaters or for the plumbing or maintaining the system. Ideally, we want water in the -3 to +0.3. And these are important also for even swimming pools. People should pay attention to this so they don't destroy their swimming pool filters and things like that as well. Now, a big question from this kind of analysis here is, what do you do if you're a private water user? You don't have a public utility checking to see if your water is corrosive or not. In the case of Flint, it was a public utility, and they thought that they could get away with not using corrosion control because they were going to switch to Lake Huron within a year of using the river, and they didn't think that the plumbing would corrode so quickly and cause so many horrible health problems. I think they thought they could get away with it. But with private water users, you have no clue of whether your water is corrosive or not. So what do you do? What do you do if you're on low income? And here's where corrosive water is in the groundwater around the United States. So all these red dots are areas where it's corrosive. Blue dots means if you're using it, it can clog your plumbing up potentially, scale forming, and then stuff that's -0.5 to 0.5, it says is indeterminate. It may also be optimal. You can see Kentucky doesn't have a lot of well water tests in this particular image. So I was asking, are you able to have corrosive water in southeast Kentucky? And if so, are the lead levels associated with those samples above the EPA, not maximum contaminant level, because there isn't one for lead. Call it an action level. There should be an MCL. That's up for public debate. Very active debate. So I'm just going to skip the hypotheses and jump to it. The data that I had from this, there's not a lot, were obtained from the Kentucky Geologic Survey, and it looked at wells and springs constructed before 1988 because even the pipes could have theoretically had lead in them. Fixtures still can have lead even for a few more decades after that, but the pipes could have had lead in them, or even cadmium. So Letcher County was emphasized in my study because I've done some work there with other programs, and 26% of the homes in Letcher County were pre-1950. 39% were built during this time between 1950 and 1979, and then over half the residents at the time of this study were using private groundwater if they were actually consuming it. And the household income is relatively low in this county, and it's a beautiful county. You know, if you go up to the top of Pine Mountain, it's probably the best view sheds in the state. What did the state's data show? And you can see the pH, you know, typical kind of range. You know, we got our alkalinity or hardness values. Most things all kind of acceptable. We got a few outliers on total dissolved solids. We got some really soft water, and we also got some really hard water, but by and large in the middle, it's pretty good. And the Langelier Index, the focus of this kind of talk here, was that we went from being corrosive, so we're well below -0.5, and we also got scale forming water. Both of those are possible from our groundwater based on the state's well water data. So remember, here are the numbers here. So handful of them are balanced. Most are actually scale forming, and only a handful are actually likely to cause corrosion of the plumbing. Lead, thankfully, was relatively low in these samples. However, there were a handful that may have exceeded it. Copper also was relatively low, but you can see a handful that are relatively high, and we'll look at what that 24 means. Manganese, overall, relatively low. 0.05 is where the secondary standard is. We see the 75th percentile being 0.27. Anything over 0.30 used to have a World Health Organization limit for it. So let's look at the lead. So lead levels below 15 are associated with no required action. Lead levels above 15 were associated with action. So there were 2 samples actually that had high lead levels in the state's database. 2 that were above 15 parts per billion, which would have warranted action if it was a public system. Manganese, there were 6 samples, or 23%, above the expired health advisory criteria. A fair number exceeded the secondary standard of 31%, but also 46% were acceptable. Was there a relationship between the corrosivity of the water and lead? So this water should actually be scale forming, and this water down here should be corrosive. And unfortunately for these folks, they have high lead levels, but thankfully it wasn't associated with the corrosive water. So I don't know why these lead levels are so high. And then copper also was high, associated with the time that the lead was high. So the copper and the lead were both high at the same time, which may suggest something corrosive is in that water. I don't know. But the indexes for these were suggesting scale forming. So I'm not going to belabor too much on these discussion items here. We've done a lot of work in this area. If somebody wanted to see if their water was corrosive, just having an iron nail test, just putting a nail in the water and see how long it takes. And then people who are worried about lead and other things in their water, would probably benefit from having access to bottled water or some other way. There's children that could be theoretically drinking this water. So I'm going to stop there on the particular presentation. But we're going to review here really quick. Important review items. So Langelier Index, negative 0.3 and worse, that's corrosive, and then 0.3 and higher, that's scale forming. What types of things are going into that formula? Higher pHs, more calcium tend to associate it with more scale forming. Lower pHs, less calcium, tends to make the water more likely to be corrosive or scavenge metals that are in the pipes. Those are important things. It can be prevented in public systems through adding a corrosion control agent. But for private homeowners with wells, it's a little bit messier and harder to work with. Private wells are not public systems. So there's not a lot of resources to get them help. So this concludes the section here on drinking water. You're encouraged to be prepared for the next step. We'll do an exam on the topic. So I'm going to stop the video here. If you have questions, you can always reach out to me. There's my email as well. All right, thank you.